Hiya! So in this video, we're going to look at an example of a transition matrix to kind of see how this kind of looks like and how we get from one basis to another. So first we're going to look at an example, or we're just going to look at examples today, or in this video. So we're going to start off with some matrix, and it'll turn out to be a transition matrix. So we're going to look at a matrix 1, 3, 7, 0, lambda 5, and 0, 0, 3. So we start off with this matrix. This looks like an S, so I'll make that into a 5. So we start off with this matrix. Here, lambda is some arbitrary vector in R. We don't really care. Lambda is in R. And we're going to specify that E1, E2, E3 is an ordered basis of V. So remember that for transition matrices, we define them using an ordered basis. So what ordered vectors, where does this go to? So what ordered basis does this map to? So it turns out what we can basically do is, if you kind of remember, and I'll give you a little cheat, if we kind of go back to the transition matrix, notice how we just have columns, right? So the columns are defining our vector, our basis, right? So in other words, all we have to do here is we look at the columns, and that gives us the ordered basis. We have to go in order. So the first column gives us E1, right? Because we have 1, 0, 0. So that's it. So that's the first basis element. Now the second basis element, we have a 3. So we have 3 E1 plus lambda E2, and there's nothing in E3, so we leave it alone. That's the second basis element. The third one is 7 E1 plus 5 E2 plus 3 E3. So this sends us to this set of 3 bases, but I don't actually know if this is a basis yet, right? And the reason I don't know is because of this lambda. What is this lambda? And so here what we're going to have to do is we're going to have to use our proposition. So our proposition 1.15 basically said that this is an ordered set of for a basis, so an ordered basis, if and only if one of these 3 things hold, right? So I mean, looking at this, you can try doing trying to find its inverse, the invertible matrix that makes this, right? You can try to find its inverse. You can try to show that it has rank n. Our preferred method throughout this class is going to be kind of looking at the determinant. So basically by proposition 1.15, we basically can just look at the determinant. So what's the determinant of this thing? It's actually really easy. So the determinant of t, 1.15, the determinant, that is not how you spell determinant. The determinant of t is just the diagonal, right? 1 times lambda times 3. So just 3 lambda. Super easy. Now remember, this has to be non-degenerate. So in other words, this cannot be equal to 0. So in other words, this works if and only if. So here we'll call this C. Therefore, C is an ordered basis if and only if lambda is not 0. So lambda is any number except for 0. And that's it. So it's an ordered basis precisely when this is true. Now, you might be at this point going, okay, you keep saying ordered basis, ordered basis, ordered basis, but like, why? Who cares? Like, what? Why? And we keep stressing it's actually very important. And here is kind of why we're going to see an example. Well, I'll show an example of why this is actually important. So this is like a massive, we'll put like little, we'll do it in different colors. Like this is a big remark on why this is important. So like without ordering the bases, we like if you look at the column vectors, we don't really know which columns things are going to run into, right? Like I could just put it in random columns and theoretically they should all be the same. But that makes things a little bit harder in like not harder. Like if you know, like if we change two columns, right? We switch their sides, the determinant changes. So we're actually changing properties about this matrix by doing that. So the ordering really does matter when we are looking at this. So for example, if I do take two ordered bases and I take E1, E2 for the first one, and I take E2, E1 for the second one. Okay? Now, if they were the same bases, right, then I should get the transition matrix be the identity matrix, right? So we'll note this. If B and C were the same, then the transition would be the identity, And here, remember, the identity in matrix forms is this matrix, right? So we should expect this if this is the identity. But the problem is, in this case, it's not. So if you calculate it, well, E2, right? So the first vector here is 0, 1. And remember, we write these vertically. And E1 gives us 1, 0. So the transition matrix is not an identity matrix. So these two bases are inherently not. There's a transition. There's a little transition from one to another. So they can't be the same. And this is why we're almost always going to exclusively talk about ordered bases. Because ordering the bases does change our vector space in some sense. So from now on, we will always, well, not always, but like almost 99.9% of the time, we will say ordered. So we will only consider ordered bases for the remainder of the course. And we shall drop the prefix ordered. So from now on, when I say ordered, or when I say basis, I mean an ordered basis. Always. You can't see that. Ordered basis. So we will go from there. Yeah, so we'll stop this video here. And we will talk about Euclidean vector spaces or inner products next time. So I will see you all then. Peace.